by examining the behavior of a minimal stigmergic agent field simulator running continuously on a two-dimensional toroidal grid. When observing scattered points clumping together on the grid, a specific professional misconception often surfaces. Observers frequently mistake this clustering behavior for advective Keller-Siegel chemotaxis. Left, traditional chemotaxis. An agent evaluates a smooth gradient stepping toward the highest concentration. Right, our minimal model. Agents execute entirely random walks, ignoring topology. The mechanism is absorptive trapping. They walk randomly until hitting a local threshold, deposit mass, and permanently freeze in place. Because of this rule, there is absolutely no gradient following or advective term written into the model's update logic. By hardening the diagnostics on this purely absorptive model, we expose a highly constrained system governed entirely by stochastic ignition and strict mass budgets. Understanding this baseline null model is necessary. It proves that massive, seemingly coordinated clusters can emerge on a grid with zero intelligent agent navigation. To understand those constraints, we must examine the grid's physics, specifically what happens to the scalar field once an agent deposits mass. The model operates under mass-conserving periodic boundary conditions and uses a perfect diffusion stencil. When a cell receives a spike of mass, that mass diffuses outward in a perfect wave. As it reaches the boundary, it seamlessly wraps around to the opposite side. No mass is lost. Because the boundary doesn't leak, exactly two global variables alter total system mass: deposition as the source and decay as the sink. This establishes a quasi-steady-state equation. The total field mass is simply a function of the deposited mass divided by the decay rate. The field, therefore, is not an autonomous entity. It is strictly slave to the fraction of triggered agents. This chart displays the mass-budget ratio over time. Comparing this to the triggered agent fraction, we see a tight visual correlation between the curves. The mass growth perfectly tracks the underlying agent supply, confirming the slave relationship dictated by grid physics. Because the field is budget-slaved, macroscopic patterns on the grid aren't driven by complex field dynamics. They're entirely dictated by how efficiently agents are captured. If the agents are executing completely random walks, we must isolate exactly what initiates the runaway trapping effect in an empty field. The catalyst is the model's primary control dial, the parameter Q, which determines post-deposit agent mobility. A Q value of 0 dictates that a triggered agent deposits mass and freezes permanently, becoming an absorptive source. A value of 1 means the triggered agent deposits mass and immediately continues moving. Every simulation run begins at a dead nucleation floor. Exiting this 0 state relies on a tiny, spontaneous seed probability to spark the initial activity. This chart graphs the triggered fraction. The Q value dictates how the system exits the dead floor. The red and gray traces for low mobility show rapid, systemic ignition. Conversely, higher Q values flatline at the bottom. These clusters never sustain critical mass. The orange trace at 0.10 exposes the marginal boundary.
Here, identical starting conditions produce noisy, highly delayed transitions. This is stochastic ignition. This delay dictates how the data is analyzed. Runs flatlining within the observation window must be treated as right-censored ignition times in a survival analysis. They have failed to ignite within 2,000 steps. They have not proved permanent failure. Phase transitions in this minimal model are not clean binaries. They are stochastic ignition time problems, controlled by retention versus decay. The high variance in stochastic ignition highlights a significant hazard in simulation methodology. Apparent complex behaviors are frequently just logging artifacts. The first methodological trap is asynchronous updating. In an asynchronous loop, agents are updated sequentially within the same computational tick. Later agents react to local fields artificially raised by earlier agents just milliseconds prior. This chart tracks the empirical damage of cross-agent reinforcement. Compare the upper red asynchronous trace against the lower gray trace, representing two-phase mode. Here, all agents evaluate a frozen field before deposits are applied, a mode mandatory to prevent inflated capture metrics. The second major trap occurs when evaluating cluster concentration by measuring the raw top one. By stripping away the asynchronous artifacts and utilizing null-corrected diagnostics, we can evaluate the system's absolute baseline behavior. The minimal model produces a critical negative result. Despite achieving admission, it fails to demonstrate any intrinsic spatial scale. The clusters ignite and aggressively bleed outward, consuming the entire screen in a saturated block of activity. This is the rule of no self-arrest. Because the field mass is budget-slaved, it lacks a mechanism to intrinsically plateau. It simply expands until it exhausts the finite agent supply. Measuring component sizes at the end of the simulation provides only a stopping time measurement. It does not establish a natural, stable attractor scale. Minimal Model version 0.2 produces excitable absorptive trapping and stochastic ignition, but it cannot intrinsically stop its own growth. This defines the explicit requirement for the next experimental phase, adding a refractory resource, denoted as R. To succeed, R must meet strict operational criteria. It must break the budget-slave dynamic, force the release of trapped agents, and generate a stable, finite-scale structural feature. Rigorous computational modeling is about stripping away illusions to establish an undeniable dead-floor null. Only against Gantt rigid baseline can true self-organization finally be measured.